Okay, for people joining this live stream starting a little bit late here, this is about neural networks and explainable AI kinds of things.
Yeah, actually, not so much neural network. I have something about neural network at the end, but it was not the important stuff.
Okay, so this is
agnostic.
Okay, so this is a way to assign causes to decisions, basically. It's a way to say why a decision was made the way it was made.
Yes.
Is that right?
Yes. Exactly.
Okay.
So,
which group of pixels can change this hound into a hare or something? Okay, I get it. I understand the point. This is okay. So this is all right. For 12.2.
Well, yeah. So this is the very, very popular way to assign contribution to features. And so you can discuss about the way it works if you want. And in terms of design, it's actually the most popular. It's incredible how it's like 3-4 years old. It already has like, I don't know, thousands of iterations. Everybody loves it. And so it's called SHAP, which stands for Shapley Additive Explanation. And the way we would use it is a property of predictor function, classifier function.
So and, just like top probabilities as a property.
Exactly. And I think the key that we figured out by exploring designs is that the output should actually have the same structure, the same container as the example. Like yes. For example, here you have data sets, and it actually, each numeric value, it replaces it with its SHAP contribution.
Well, I might argue that you should add another column, but I don't know whether you. What do you do in the case of pixels, for example?
Exactly. That's the thing. So this is a. We haven't implemented the pixel one, so this is just.
Well, that's cute. Yeah, so you're using color level.
Exactly.
And although you probably should use a black-white level because that way you can just read it out directly.
Except you have negative and positive, so it's important.
Do we have somebody from the image processing team here? Can somebody comment on it? It's not obvious to me how you should do this.
Yeah.
I think have somebody from the image processing team?
Matrix plot does that pretty well.
Okay, I'm asking because it's going to be you're trying to make it an array. Yeah. Why don't we try and find Shadi or somebody else from image processing, please?
Sure, yeah, we'll try to grab them.
Because if you're really going to do this write back mechanism, right, it's got to actually work.
Oh, okay. You mean for the image, okay.
Yeah, right.
I was just saying for the style.
Yeah, yes. Yeah, the problem is it is just an image then, right?
Yeah.
And I don't think you should call it explanation. I think what you should do is call it something like what should you call it? Because I can imagine that one wants to put these two things together here. The actual predictor and the, it's like top probabilities. It's like in top probabilities, you have the actual things and you have their probabilities.
Which you do here, fixed acidity, that's contribution, volatility.
No, I understand. Yeah. But these are the values that have come out of the predictor, right? And this is the assignment.
Those are yeah, that's one example. We're figuring out how much each feature in the example contributed to its prediction.
Well, I'm sorry, but by the way, can you adjust your audio, please, Jesse, so that we don't hear a bunch of background nonsense? Okay, what does this actually? Okay, so here we go. Let's just run this again. This is supposed to run in 12.1 or not?
No.
then
No,
I
no.
asked you that at the beginning of this meeting. You said it
And I
didn't matter.
said there's nothing to run.
Oh, and there's nothing to run at all. So I can't run this
No.
at
I
all.
mean, yes, in Jesse's thing, there's something to run, but that's it.
Okay, all right,
And,
fine. But then, so this is making a predictor function. The predictor function takes
Yeah.
what as input?
This is one example.
Now, I know. So it's taking this association as input, right?
Exactly. An
Okay,
association or
what's the
data set.
output? What is the normal output?
The output is a number, one number.
Okay, all right, okay. So this is the explanation for that one number. Just like if I
Exactly.
say, okay,
Exactly.
right. So if I do this and I say image identify of that thing, comma, and then I say, I don't know, top probabilities. Is that an option for image identify?
Don't think it's like that.
Okay, so let's say I say classify
No.
this as a notable person, for example.
Yeah, this will work.
Right. It'll give kind of a stupid answer. Right? Who knows what it'll say? Who it'll say that is? Why is it so slow? By the way, I've noticed, and particularly in 12.2, I've noticed really slow initial.
I mean, this is not that, I think. I mean, actually, it might. But no, you would see a download thing. I think it's the display of the entity.
Okay, all right. So here, what it's doing, it's not very confident of any of them, but this is the same type of thing. This is giving the entity and its probabilities, right?
Mm-hmm.
So in principle, here, you could want all three of those things. You could want the wine it had identified or whatever it was, right, for classify. You can do this for classify presumably as well, right?
Yeah.
Okay, you might want three things. You might want what wine it identified, what probability it assigned to that, and for that result, right, you could have this explanation array. Is that correct?
Yeah. And you can put that in the list if you want to have the three in one shot.
Right. And what's this average down here?
This is not supposed to be there.
Okay, all right, fine.
This might be the total. Maybe
Okay,
the total. Actually, we could. No, that's not supposed to be there.
So average, it's the average wine quality across the data set. And
So it's actually the prediction.
That has nothing
right?
to do with
No.
this.
If you add the entire column, you will get the predicted quality of that wine example. This is the additive part of the Shapley additive example.
I'm sorry, adding these numbers, I'm not as challenged arithmetically as the younger generation probably. Adding those numbers does not give this.
Correct. If we add all of them, including the average, then we get 5 point something or 6 point something, which is what we would get if we put this example into the predictor function itself.
Okay, so I'm trying to understand then what these numbers mean. So
if we had a linear model, it's just these are the coefficients of sort of like the coefficients. So if we took the example, this wine, put it into our predictor, it might estimate a wine quality of 6. And what is contributing to that 6? Well, it's starting with nothing else. The average quality of wine is 5.87. And then the fact of each of these features adjusts its prediction slightly. And we can see how much each feature adjusts.
I understand. So in the case of an image, what's the analog of average there? It's some kind of, mushy gray of all the images that were in the training set, or what?
It's about the output.
If it's classify, then it would be the prior probability of that class.
Classify that.
So it's about the output, right? It's nothing about the input, this average.
Yeah.
By the way, for classify, you have to specify a class in classify, by the way.
But you have to specify a parallel probabilities, because otherwise the average is absolutely meaningless, right? The a parallel probability of each output. If there are 10 possible outputs, digits, let's say, each digit occurs with equal frequency, then the average digit is 5 or 4.5 or whatever it is, right? Am I correct?
Yeah.
Okay. But if they don't occur with equal frequency, then obviously it's not that. And
Yeah.
this is then saying, so if I did a classifier for digits, is this explanation system, it's something which can work with categorical data, right? Is that correct, or is that not correct?
Yes.
Okay, but so when it says the digit is 3, for example, the average digit is 4.5.
The average probability of having a 3. So we would run one explanation for why it thinks it's a 3. We could have another explanation for why it doesn't think it's an 8. And that's actually an example from that we have.
Okay, fine, but then I don't understand what this average is again. Okay, so in the case where it says it's an explanation for why it thinks it's a 3, what is the average? The average is what? The probability for it being a 3?
Yes.
But that's not what this is. 5.87 is nothing, is not a probability.
This is a predictor.
Just a number. This is about predictor. It's not about classifier.
Okay, so wait a minute. So wait. So you're talking about two completely different things. One is in the case of a classifier, right? You're talking about this thing is going to, there's an a priori probability for each outcome. For an outcome. Whereas in this case, in the predictor, there is, oh my gosh, something completely different. So, I mean, the analog of the a priori probability for an outcome will be a PDF, right? A PDF of outcomes.
Yeah, but yeah.
Right? But instead, so that's the real analog of these things. Right?
I mean, I don't. Okay, for the classifier, maybe Jesse can tell me. I don't remember exactly how this works, but it's about log probabilities, I guess. And is it the exact? Okay, if I take the log probability for the class 3, is it the exact same thing as the predictor?
Yeah,
explanation for a predictor.
I think that should be an analog. Yeah.
Okay, so I think what it is, so it's better to understand it just for a prediction. So 5.8 is the average wine quality, and all these values are the deviation from the average that are implied by each feature. And if we take classifier, we would look at a specific class, let's say the class of the digit 3, and we would look at the log probability of this class and treat it exactly like it's the predicted value. So we'll take the average of the log probability of being a 3. That's your average. And then all the these sharp explanations are the deviation from this log probability.
So in other words, in that particular case, really the thing I'm looking at is a probability or a log probability. And this explanation, so really what would happen there, in a sense, it's, 3 arrow probability, 0.76. And then there's a sort of an explanation of that probability. Is that correct?
Yes.
Yeah. Actually, I say log probability, it's the odds, really, right? So it's a bunch of log odds ratio or something like that.
Okay, all right. But the basic point here is, the way to think about this is, in a simple-minded way, we might say there is a, we might have a number, like this, where it's a plus minus thing.
Mm-hmm.
Whereas what this is telling us, it's kind of a story of what's behind this number. For every number, and this applies only to numbers, is that correct? I mean, ultimately, this explanation is about numbers. So it's about probabilities, it's about prediction values, it's about numbers, correct?
Exactly.
Okay. So, but in an image, it's somehow about probabilities of pixels or weights of pixels.
No.
Well, what's this picture then?
Each pixel is a feature. So it's still about numbers. It's still about
No, I
taking
get
the
that. I get that. I
probability.
get that. Right. But so I see what you're doing is you're saying, I see you're computing the probability of a particular identification for this thing, that it's an 8 with a certain probability. And then this is saying, what are the linear contributions of the different components of that input to contribute to this output?
Yes.
Yeah. Not sure about the linear part, but yeah.
Okay, fine. But so then what we're saying is, okay, so what we want to get out, what is an analog of this? Okay. So you've got your input and it has certain components. Now you're replacing every component with a weighting for that component. I'm curious, and something like
Exactly.
I'm when I think about some more linear algebra thing, like PCA or something like this, or eigenvalues or something, I don't really know. To what extent can I think about, I'm a little bit confused here, but I'm trying to understand this. I put in a vector, I get back these weightings. When do we have an analog of that situation? You put in a vector, and what you get back is weightings associated with something for that vector. Like a trivial example would be a projection, right? If we say projection of the vector 4, 5, 6 on the vector 1, 2, 3, let's say a 1, -1, 2, for example, right? That's in a sense the components of this vector. That is saying, what components of this vector lie along those directions? What in the contribution to. I'm now a little bit confused here, but do you see what I'm saying?
Yeah.
Right. So I'm trying to ask, of the thing that is going to give whatever value it is,
one thing
what
to realize
contributes
is it's a different space. It's like fixed acidity to 7 in whatever space, but the result is in the output space, so to speak. So it's a bit weird in the sense that, and also a categorical variable, for example, is still going to have a numeric contribution.
I understand, but the reason for that is because the real contribution is not to the thing itself, but to its probability.
Exactly, or predicted value, yeah.
Right. So
I think it might be better to think of it in terms of conditional expectations rather than weights, because we don't care. We would be saying, what is the expected predicted wine quality conditioned on this particular acidity? And that's how much it tells us how much the expectation changes based on that condition.
It's true. In terms of design, it's a little bit interesting, let's say. Like the image, for example, if we keep the value as they are, I wonder how we can make an image that looks good as well. And
that's a separate problem. Let's worry about that in a minute. First of all, we want to understand what the heck the thing is, okay? What it is, see, the thing that is confusing to me is you're saying two different things. For a predictor, you're saying these are contributions to the actual numerical value of the prediction.
Yeah.
Right? Not to the PDF of, the contributions. See, the analog would be, right? Yeah, I understand. But because the predictor is the what is it? Is it the mean of the PDF, or what is it? It's the expected value in the PDF, right?
Yes. I mean, depends. You can have a different utility function, but actually by default, it's the mode. It's the most likely value.
Okay. All right. Okay. So it's the mode of the distribution. So then what's happening is, in the categorical case, I'm so confused here. The categorical case, you've got a bunch of different probabilities. In a sense, the mode of this distribution is the one you pick first. It's the one with the largest value.
Yes.
Right? So
Yes.
in this case, what you're doing is you're explaining why that probability gets the value it gets. Right? And okay, what is the analogy in the case of
it's true. It's two different things. I agree.
I
In the
don't think it is
predictor,
so
we would
different, Etienne. I think that there's a way in which it's the same, but we haven't quite understood it yet. Right? So, right, I think the other case, the continuous case, is you have a probability distribution and you're saying the mode is being adjusted by these, the mode is being explained by these things. It's contributions to the mode, but I don't understand that. I don't understand how that works.
I think you could look. I think, as usual, when it's in the continuous, you could connect the two by taking a segment, an interval. I think you can have the same thing as we do for the classifier, like what is the explanation for the class 3, to do it with an interval on the output prediction for a predictor, for a regression. You say, like, what is the probability? We're going to explain the probability between the value 1 and 3.5.
Okay, let me make a difference. Okay, we have two separate functions, classify and predict. Why do we have two separate functions? Answer, because they actually work a bit differently. One is continuous, one is discrete. So my claim is, if this property happens to be the same property in the two cases, so be it. But, you know, I think conceptually it has slightly different names in the two cases.
Mm-hmm.
You see what I'm saying? Conceptually, it is, in one case, it's the explanation for the probability. In the other case, it's the explanation for the value. Am I right? Or you said the odds ratio, not the probability.
Odd ratio, and each of them, I think, is an odd ratio. And I think that's yes, I think that's correct.
Okay, let me look at some of these other ones. Okay, so this is another numerical quantity, numerical thing. Is that correct?
Also, one thing, sorry to finish.
Yeah.
In a classifier, by default, it would give the explanation for the predicted class. That's what we were showing before. And in our design, you would be able to specify which class you want an explanation for. So by default, it's
class. It tells you as the output, as opposed to. But I mean, but telling you as the output is simply the top, the mode sense of this.
Exactly.
But I mean, we could say, why is this pink? Whatever this is, I should know. I'm just not very culturally aware about these kinds of things. It looks this is a bit pink. Okay, well, I'm going to guess that she has some sort of pink story, which is why it was identified as the possible person that that's a picture of. Okay. What am I trying to say here? So you're saying I can ask, why did you think pink wasn't the thing here?
Deviate from the baseline probability as a way to see.
Right, but so for the predictor, you could as well say, you've said the prediction is 3.6. Tell me why it isn't 7.4.
Yeah, you're right. And especially if you do an interval, that would.
Right, but even tell me why it isn't 7.4. In other words, it's like I really thought that I should adjust this. I don't know. Why am I thinking of autonomous tanks? I shouldn't be, but you know, whatever it is, adjust this thing to, you know, I estimated 7.4, but the machine told me 3.2. Explain why you don't think it's 7.4.
Mm-hmm.
See what I'm saying?
Mm-hmm.
And that seems like as useful a thing as why didn't you think it was pink?
Yeah. I mean, conceptually, it's right. In practice, prediction are usually unimodal, And I mean, they can be bimodal sometimes and so on, but generally they are well explained by just their, I mean, well described by just the mode. And where classifiers can be like, of course they are.
Well, we presumably, you know, learn probability. I mean, oh my gosh, learn distribution is what gives you the actual shape of the distribution. Is that not correct?
For what?
For a predictor.
The prediction of a predictor?
Yeah.
No, it's actually of all the methods we have, they predict normal distributions.
I see.
It's,
okay.
Yeah.
Okay. All right. Okay. Fine.
That's why, yeah, it's usually like that with prediction. That's why there's often a trick that when a distribution is multimodal, people, they actually discretize the output and then run a classifier on it, train a classifier on it,
all right,
rather than parameterizing.
Let's just to understand, we're going to run out of time here. So just to understand what's coming next, okay? So these are alternative explanation frameworks, is that correct?
Yeah, yeah. This is a very intuitive one. I mean, both of them are very intuitive. We can start with adversarial example. Everybody, I mean, well known, right? Find just the closest example, or many of them, that change the decision. We don't care if it's a realistic example. So, you know, if you just have some weird noise or some blurring or some, these are not real, by the way, just your example, as you might guess. Yeah, so just modify
but so example. Now, hold on a second. I mean, just like top probabilities, in general, we might want multiple adversarial examples, yes?
I think so, yes. Yeah, by default, it would be how to change decision, but then you could say how to make it more cat, more, you know, less cat. Okay, so
for the neural net case, you're saying what? It'll show activations, layer?
I think, yeah, that's going to be a completely separate thing. And I don't know, like I haven't thought too much about design, but basically you will specify which layer or which neurons you want to activate. And that will show the input, plus some constraint, like you need some constraint.
No, that's not what you want. What you want to know is which layer, right, was activated in what way. Isn't this? Go ahead.
That's okay. That's depending if you care about understanding the model or particular decisions. So indeed, what you say, I think it's for particular decisions. Like you give a, I mean, you give an image, give an output.
Why did this thing think it was a goose? Yeah. Okay, because layer 7 had a high degree of activation in the orangeness of its beak or whatever.
Yeah. What you see here is something different. It's not about a particular decision. It's the model in general. Let's try to understand the model. So
yeah, that's
if
different.
I activate that,
that's completely different. That's completely different.
Yeah.
I mean, what we're dealing with here is why did you say that? Basically, for the model.
And I think, except that it can be also used to understand the model. This is why you say that when you apply it to a test set, right? You apply it to a test set and then you do statistics.
Fine, but I think that's a slightly different thing. I mean, the main issue is the main pattern to all of these is you said blah. Why did you say that?
Yeah.
Right.
I mean, that's
And so what you're saying is what you want to do. So some of these give different kinds of output. Like, right, so these ones here are just, what would I have had to give for input so that I would, what would I give for input that is close to the input I actually gave that would give a different answer, right?
Yes, exactly. And these two are very connected. The only difference that counterfactuals is trying to find something realistic. So it cannot have,
I get it.
You know,
an
image that is not a real image. Yeah.
Right.
Exactly.
The goat can't have can't be some kind of alien goat.
Exactly.
It's got to be a terrestrial goat or a terrestrial animal of some kind. Okay. Anyway,
Yeah, so it's just same thing, but for classifier measurements. And we can get the explanation for all the example in the test set.
All right.
And maybe some extra thing. There's one thing about names.
Yeah.
Because at first I wanted to call it the full name, Shapley additive explanation, so it was fine. But I realized that if we introduce LIME, well, the full name is local interpretable model agnostic explanations.
Yeah, it's crazy. It's crazy. Look, I mean, it's got an abbreviation. That's what we use for many of these.
Yeah,
things.
okay, yeah.
Let's just
call
use
it SHAP. Okay, cool.
Okay. So again, let's go back again to what this is actually doing. So just like you can say for classifier probability, okay, we've got a triple-barreled thing that can come out here. The thing it classifies it as, the probability, and the explanation for that probability. Is that correct?
Yeah.
Okay, so what would be our way of specifying? I mean, it could be something like, I don't know what top probabilities explained or something. I mean, how do we, or is it the case that if I say top probabilities here and I also say something else, what other property could I put here?
You can. You mean something? There you go.
Decision.
Yeah.
Okay, so there we go. Okay, so fine. So you're saying that this would be SHAP values here.
Or just could be SHAP value, or I guess there's many of them. Yeah, SHAP values, or just SHAP.
I think we should call it SHAP values. I think it's going to be more confusing.
Yeah,
I think some of these other things are not going to be just values.
Yeah, it's
going to be distributions, and because that distinguishes from adversarial example, things like that.
I agree. The only downside is something called Shapley values, which is related but different, and but I think that's fine.
That's why people can spell. I mean, there's Shap and there's Shapley. I mean,
yeah.
Okay, so then what we would do here is we're feeding back into the original format. So if the thing that was given as the original format was a list, for example, right? If instead of a data set here, it was a raw list, 56875 was the actual data, that data will be replaced by the corresponding SHAP values. Is that correct?
Yes, which is going to be the most common case.
Okay, so what we're saying here is that, again, the triple-barreled case of decision, probability, SHAP values. You see what I'm saying?
Mm-hmm. Mm-hmm.
How do we represent that? Or don't we? Or do we just say top probability SHAP values to get this list and a corresponding SHAP values list?
That would be a lot of. I don't know. I don't know if in practice people are interested in all the SHAP values.
Well, otherwise, what you've got to do is to say something like SHAP value for, in here, you've got to say SHAP value arrow. I like the pink one wherever the pink one was.
Exactly. That was our proposal. Yeah.
For this. So to say, is it like this or is it in a list? It probably is in a list.
No. It's we abolished the list because they are used for having several properties.
Oh, okay.
Like we do that for top probabilities. You can put arrow 5, let's say. You have the top 5. And yeah, we also do that in classifier measurements.
Okay. All right, fine. So then SHAP value arrow pink would give the SHAP value information for
exactly.
that.
Yeah.
Okay. All right. Now, the remaining thing is, as we push stuff back into the data structure that we were given as the actual instance, how do we do that for images? Or how do we do that for audio? What do you want to do for audio?
Yeah, I thought about that. I mean, I guess it would work the same.
Shadi, do you understand? Shadi, do you understand what we're talking about here?
I'm not very familiar with these. No.
Okay, so what this is a sort of blame assessment for different attributes of the input. Which attribute was the most important in determining the specified output? Okay.
Mhm.
So in this case, the explanation that this was an 8 or something is, or wasn't a 3 or whatever else, we're assigning blame a number in this particular case between -1 and 1. Is that correct? Is that correct? Not -1 to 1?
No, it can be more than that, yeah, or less than that.
So it's an arbitrary value.
It's an arbitrary value, yeah. I mean, if you're predicting things that are very big, which it's true, gave me concern for this image. It was a great idea, but it's.
All right, so Shadi, so these are unbounded numbers, positive and negative, right?
Right.
So the question is there any reasonable way to represent that as an image, or should what we do be to just give the array of numbers and you can wrap image? I mean, if you wrap image around an array of numbers that range from -2 to 18, what is it going to do?
It just shows you stuff between 0 and 1 by default.
Okay.
And you can image adjust it if you want to see more of it.
Okay, well, that doesn't seem like a good thing to do by default. I mean, in other words, so okay, to encode those values just seems, yeah, I think we're not going to be able to do this, right? So
you're concluding an image is better? I think array.
No, array is
Yeah.
better. That's what I'm concluding.
Right.
I'm concluding the image is hopeless. Because although it's cute, I think it's necessary to say either matrix plot or some such other thing around it.
Mm-hmm. And remember, we have numeric arrays if we want it to be cuter than just an array.
And what does that do for us?
Well, still can store the numbers, just instead of a dense array that is large, it's going to look like a summary blob.
And what happens if I say array plot of a numeric array? Does that work?
Yeah.
Then that's what we should do.
There are a bunch of other things that don't yet work, but it's in the pipeline. Mark was working on getting arithmetic.
Matrix plot.
Matrix plot works, yes.
Okay. Well, then I think that's a reasonable thing. In worst case, you say normal of the numeric array.
Mm-hmm. Correct.
I think that's the right thing to do. For images and audio, I have no idea what we do for video.
Now, for audio, the most common feature to use is not the audio data. It's typically MFCC that goes in as features, and it could have variables to specify how large or small the MFCC should be in both dimensions. Etienne, have you given this a thought? What should we do? Should we always assume it's MFCC with some predefined preset?
Hold on. I'm now very confused by something. This thing, in general, if we had an encoder, a data encoder here, is this explanation? Well, okay, I'm sorry. So this
before the encoder.
This is before any encoding. Okay.
Yeah.
But does it make sense for audio to do it before any encoding? Because the frequency data is very important there.
Yeah, I haven't thought so much for audio.
Okay.
We probably have to have a different case for audio.
Okay.
Yeah.
I don't think it's going to work for just the array.
I don't think so either.
Yeah.
Okay. All right. Anything else we need to figure out for this meeting?
No, I think that was it. That was it.
Okay, this is cool. It's good functionality. And
Something they've been asked
right.
a lot as well.
Sounds good. All right. Okay. For people following this live stream, we are about to go to another live stream on geometry and graphics features. So hope to see you there. Thanks, Etienne, Jesse,
Bye-bye.
Shadi, etc. See you
Apple.
later.
Thanks.
Okay.